Today what I want to do is I want to do a little bit more graphing practice. And specifically, we're going to continue graphing quadratic functions. What we're going to try to do here is show you some shortcuts, or take some shortcuts in this whole process. Because there are techniques that you can use and long methods that can be done to, complete the square and check all of these in different ways. But there are different things that you can notice about these different types of functions and maybe what method you might want to use in order to graph it as quickly as possible. So today I have two functions here that I want to graph. And so what you might notice is the difference between these two is, well, first off, there's a negative coefficient in front of the x squared here, and there's a positive one here. And so that leading term, the coefficient on that leading term, really what that tells us is whether the parabola is going to be, flipped over and kind of have an upside down U shape, or if it's positive here, you know that it's going to open up. So when this coefficient here is negative, then this is going to open down, and when it's positive, it's going to open up. So that's one thing to take into consideration when looking at these. The most obvious thing, though, that I notice is in this function, the constant term is missing. You can see here the constant term is 1, but here there is no constant term. And so what we're going to do with that is we're going to recognize a simple way that we can graph this without having to use transformations or necessarily need to do any complicated calculations. And so let's actually move closer to that one. So I see that there's a constant missing here. And anytime we're working with polynomials, so a polynomial is just any sort of algebraic expression that has many terms. A quadratic function or equation is a polynomial. If we can factor this thing, what we can do is we can find where the graph crosses the x-axis or the x-intercepts. And quadratic functions have a very special property around finding the intercepts and also finding symmetry around different points. Because a quadratic equation gives you a parabola as a shape, then it's going to have a sort of symmetry around its vertex, and it's called even symmetry. And so this symmetry is going to help us kind of find that vertex, because between those two x-intercepts that I find, halfway between is always going to be the vertex. So for all quadratic functions, the halfway marker between the x-intercepts is going to give you the x-coordinate of the vertex. And then once I know what that x-coordinate is, then I can plug that in and find the output. All right, so let's do the math here, and let's figure this out. In order to find x-intercepts, the definition is that the output is going to be 0 for the value of x that we're trying to find. So here, my output f of x, I'm going to set that equal to 0. And what I'm going to do is I'm going to try to factor this right side of the equation here. Well, the reason why I'm doing that first here is because this kind of equation is much easier to factor without that number on the outside. If I look at these two terms here, I have a greatest common factor. And the greatest common factor here is just going to be x. But before I do that, let's actually take out this negative here. And so that's going to help me a little bit. I'm going to take the negative out by factoring out technically a -1. So negative times x squared is negative x squared. And then negative times negative 6x, that's going to have to be plus 6x. Okay, I want to get rid of that negative. I could have done that by adding x squared and 6x on the other side and making this side 0, or I can show it this way as well. Well, if I divide by negative 1 on both sides here, 0 divided by negative 1 is just 0, so that negative on the outside now no longer matters. And so I can erase that negative, and now I just have x squared plus 6x equals 0. And now the greatest common factor between these is just x. X times x is x squared. And then x times 6 is going to give me 6x. So now I've factored this function by just taking out x and dividing by negative 1 on both sides. Well, if you remember, anytime we factor an expression and we set it equal to 0, well, this says that x times the whole thing x plus 6 is equal to 0, which means that x could equal 0 in this case, or x plus 6 could also equal 0. Well, if x is equal to 0, then we know that one of my x-intercepts is at x equals 0. And then if x plus 6 equals 0, well, negative 6 plus 6 is equal to 0. So we have x-intercepts here at 0 and negative 6. All right, let's now draw this graph. Okay, and I might have to extend that a little bit because I don't know how far that's going to be. Okay, where this graph crosses the x-axis is going to be where x is equal to 0. So I'm going to have a point there. And then it's also going to be at 2, 3, 4, 5, 6. So at x equals negative 6 here. Okay, so this is where the graph crosses the x-axis. We know that this graph is going to be pointing, it's going to be opening downwards. So it's going to be kind of an upside down U. And we know that because the leading term is negative. So what else do I know? Well, I said earlier that between the x-intercepts here must lie the vertex. And so when we look at halfway between 0 and negative 6, that would be x equals negative 3. So I know that wherever the output of this function is at x is equal to negative 3 is going to be the output of the function. And so when I plug in negative 3 into this function here, what I'm going to get, f of negative 3 is equal to negative 3 squared minus 6 times negative 3. All I did is just plug in negative 3 for x here, and I'm trying to determine its output. Negative 3 squared is 9. And then this negative 1 times 9 is going to be negative 9. Negative 6 times negative 3 is going to be positive 18. Well, negative 9 plus 18 is just 18 minus 9, or 9. Okay? So 1, 2, 3, 4, 5, 6, and I'll extend that. So 6, 7, 8, 9. Okay. So when x is equal to negative 3, my output is negative 9. And because this graph must cross through those points along the x-axis, you can see that the trend is going down, and we've confirmed our initial assumption here. Well, what about this one? Well, we could try to figure out if we can factor this and find the x-intercepts. But what I like to do with this is I like to find the vertex first. And if you were to complete the square here, you would find that. You would be able to turn this into a function that looks like a transformation. But let's find the vertex first using the formula h equals negative b over 2a. What that h is the x-coordinate of the vertex. And when I look at the coefficients here, ax squared plus bx plus c, my b is going to be negative 4, so the negative of negative 4 is going to be a positive 4. And then a is 2. 2 times 2 is just 4. So the x-coordinate of my vertex is going to be at x equals 1. In order to figure out what the y-coordinate of that point is, I can plug in 1 in for x here into the function and figure out what the output is. So basically I'm going to evaluate f of 1. So f of 1 is equal to 2 times 1 squared minus 4 times 1 plus 1. Well, 1 squared is just 1. 2 times 1 is 2. Negative 4 times 1 is negative 4 plus 1. 2 minus 4 is negative 2 plus 1 is equal to negative 1. So my vertex is going to be at the point 1, negative 1. And if we turn this into a function that looks like a transformation, well, remember that our blueprint here for any quadratic function is going to look like this, where a is basically how much it's getting stretched by or compressed vertically, and then h and k is our vertex. Well, we know that the h value is 1 because that's the x-coordinate of my vertex. The k value is negative 1 because that's the y value of my vertex. So we can plug that in for h and k. And the a value here, if you were to complete the square on this, actually matches up with the same a value that is in the original equation. So if I were to write this function as a transformation, a would be 2, h is 1, so this is x minus 1 squared, and then k is negative 1, so minus 1. All right, so that's what this looks like. The thing is if I know the vertex here, and I have one other point on this graph, then I can kind of skip this whole process without having to worry about transforming points. And the way that I can do this is I can find a really easy point on the graph. Well, one of the easiest points that I can find is when x is equal to 0. Because notice that when x is equal to 0, these two terms cancel out, and I'm just left with the constant at the end. So if x equals 0 in this function, then the output is equal to 1. So I know I have a point there. And now I have the vertex from what I had previously. The vertex is going to be at 1, negative 1. Well, because this vertex gives me an axis of symmetry, what this tells me is that if I move from the vertex to this point, the same distance in the opposite direction, it's going to give me the coordinate for the next point. And so the vertex is at 1, negative 1. I have to move left 1 and up 2 in order to get to this point. Well, that means that there must be another point that is completely symmetrical across this axis of symmetry here. So if I go left 1 and up 2 here, then I must need to go right 1 and up 2 here in order to get that other point. And I could find other values as well here, but I really only need these 3 points in order to graph this quadratic function. The a term is positive, so this is going to be opening upwards. But rather than having to use this, or even use the original equation and plug in a point and calculate its output, and then use the symmetry, one of the easiest points to calculate is just the y-intercept. And for the most part, because this graph is continuous, you're going to have a y-intercept somewhere along this graph. So it's just a much quicker way to graph this rather than going through this long method here and doing transformations. So just to recap, if you don't have a constant on the end, it's easy to factor, find the x-intercepts, and then realize that the vertex is halfway between the x-intercepts and figure out what its output is. If you're given a quadratic function, find its vertex. Quadratic function, with a constant value that may not be so visibly easy to see in terms of factoring and doing this quick method. Find its vertex, calculate this out, and then if you have the y-intercept and you have the vertex, then you can find the other point that's on the graph and easily graph it. It's much shorter than going through the transformation method. So I hope that helps. If you're asked this kind of question and you're limited on time, maybe for SATs, it's good to have some of these quick methods to try to figure out, how to graph this and what your answer might be. As always, if you have any questions, feel free to leave a comment below. If there's any topics that you want to cover in these sorts of videos, let me know as well. And make sure that you subscribe so that you can see more math content.